0. Okay, because the value of dV is 0. The second one was constant pressure process, in which the pressure is constant, P is equal to C. It is also known as isobaric or isopistic process. We calculated the work transfer using this particular equation, delta W is equal to PdV, and then we got the expression W1 to 2, that means W for the process 1 to 2 is equal to PV2 minus V1 minus PV1, and then we have written it in this fashion, PV2 minus V1, which is also equal to MR T2 minus T1. Then this is the isothermal process. Isothermal means temperature is equal to constant, and when the temperature is constant, this term on the right hand side MRT becomes constant. So we say that the value of P into V is constant, or P1 V1 is equal to P2 V2 is equal to P3 V3 is equal to constant. This is what we got. And when we calculate the value of the work, I told you there are various equations which we can use here. This is the value of the work, P1 V1 log natural V2 by V1. Because now P1 V1 is equal to P2 V2, I can use P2 V2 also here, log V2 by V1, same expression. Then P1 V1, is equal to MR T1. Okay, so we have used MRT1 here in place of P1 V1, and similarly instead of P2 V2 we can use MRT2. We also know that P1 V1 is equal to P2 V2, so it means that V2 by V1 is equal to P1 by P2. So that means I can replace V2 by V1 by P1 by P2. So that is what we have done in the next value. W1 to 2 is P1 V1 log natural P1 by P2. So here instead of using V2 by V1 which is used here, we have used P1 by P2 because that is equal to that from this particular equation. Okay. So there are various equations which we can use for calculating the work. I think somebody wants to join, so just wait for a minute. Okay, so we have different equations. The first equation is P1 V1 log natural V2 by V1, which is also equal to P2 V2 log natural V2 by V1, and this is equal to MRT1 log natural V2 by V1 equal to MRT2 log natural V2 by V1. So in any case, what I can do is I can always replace this V2 by V1 by P1 by P2 in every equation. So I have in total 8 equations for the calculation of work transfer in case of a isothermal process. Now, one question was asked from me just before the start of the lecture. The question is, when I calculate the value of 1W2 for a isothermal process, okay, for the isothermal process, the value comes out to be negative. So when the value comes out to be negative or say positive, what is the meaning of that? So there can be two things. The answer comes out to be negative or answer comes out to be positive. Okay. And what is this W1 to do? It is work I can write it as work transfer for process 1 to 2. Okay, so it doesn't tells me, this terminology doesn't tells me whether the work is done on the system or it is done by the system. Okay, so I don't know. Now let us, I hope you remember the sign convention for the work. Now let us see it here. Suppose this is the system and work is going from the system to the surroundings. Okay, so work is, this will be known as work done by the system and the value will come out to be positive. So work done by the system is positive, whereas if the scenario is different, for example, this is the system now and the direction of the work transfer changes. So it is from surroundings to the system. So system is here. Now this is work done on the system, and this work is known as, this work is actually negative work. Okay, this is negative work. So it means if in the question, if you are calculating the work transfer and it comes out to be negative, you should not worry about that. Negative means it is work done on the system. Okay, so it is, sometimes we have certain devices where we have to supply the work from the outside. So that work is actually the negative work. And if we get the work from the device, then that work is the positive work because that is done by the system. So I hope the answer is clear to you. Your question is clear.
Yes,
Okay,
yes,
let us
teacher, very well.
proceed further. The next process is reversible adiabatic process, and in this particular case, I would like to tell you what is the meaning of adiabatic first of all. When I say adiabatic, adiabatic means no heat transfer, no heat transfer from the system to the surroundings or from the surroundings to the system. So it means if this is the system, okay, so the value of the Q will be equal to 0, or if it is coming into the system, then in that particular case also this is equal to 0. So neither the heat leaves the system nor the heat enters into the system. So that is a adiabatic process. Now we have to calculate the work transfer for this particular case. Now first of all, we have to draw this particular plot actually. Now for the time being, you can consider that this is the initial state. Okay, if you draw a constant temperature process that goes along this line, so this is the constant temperature process. If I draw or plot a PV raised to power gamma is equal to constant, which is a reversible adiabatic process, in that particular case, it follows this particular path from 1 to 2. So this is the path for the reversible adiabatic process. That means a reversible adiabatic process has a steeper slope. The slope part we will discuss later on. For the timing, I have drawn both the processes on PV diagram so that you don't have any problem in understanding later on. Now we have to calculate the value of delta W is equal to PdV. Okay, we have to calculate the work transfer which is given by this particular equation PdV. So now you see in this particular equation there is P. So this P is to be replaced by V. Okay, we know the relationship between P and V. We want to replace this P by V. So this is the relationship here. So what I will do from here, I will calculate the value of P. Now P will be equal to C. This comes in the denominator, C divided by V raised to power gamma. And if I take in the numerator, it becomes V raised to power minus gamma into C. Okay. Now this is what I can put in this particular equation here. Here I can use this value of P. So you can see it here. Now I will see W1 to 2 is equal to V raised to power minus gamma, which comes from this equation, because this is the value of P. Okay, this is the value of P into dV. Okay, so it is P, this part is P, and this is dV. So both the things are here. And one more thing, here it is written that gamma is Cp by Cv. And what is Cp by Cv? It is the ratio of specific heats. So we will discuss about the specific heats later on this particular chapter. But for the time being, you should remember this. I think it's clear to you up to this particular point. Here it is clear to you. Now we are going to proceed to the next slide. So this is the value of W1 to 2. So C being constant, you can see the previous slide once again. C is here. This is a constant term. So this can be taken out of the integration sign. So here it has been taken out of the integration sign, and we are left with V raised to power minus gamma into dV. Now I hope all of you know the integration part. So we can integrate it, and the integration is given by V raised to power minus gamma plus 1, because we have to add the power and divide by the same power. And then here we are putting the limits from 1 to 2. So this value is 1 minus gamma. This has been taken out of the brackets here. C is already there. So inside we are left with V2 raised to power minus gamma plus 1 minus V1 raised to power minus gamma plus 1. Okay. Now what we can do in the next step is we can shift both constant and 1 minus gamma inside the bracket. So here you can see this C comes inside, this C also comes inside. Now we know that this relation PV raised to power gamma.
Te- Teacher,
Yes,
gamma it's a constant.
yes.
It's a constant.
See, gamma is the ratio of specific heats. The value of gamma is equal to Cp by Cv. Okay, just wait. I will show you.
Mm,
I have written some. Okay, I think I have discussed previously also that gamma is the ratio of specific heats, and its value is equal to 1.66 for a monoatomic gas. Okay,
yes.
and its value is 1.4 for a diatomic gas. Okay, and its value is equal to 1.33 for a polyatomic gas. Okay, and this Cp by Cv, Cp is the specific heat at constant pressure. Specific heat at constant pressure, and Cv is specific heat at constant volume. Okay, so this is how we know about the value of gamma actually. Now what we can do here is, in this particular equation I can put the value of C. So you can see this value is actually equal to C. So here if you see V2, and C can also be written in terms of P2 and V2 from here. Okay, so here for this C I am using P2 V2 raised to power gamma multiplied by V2 raised to power minus gamma plus 1. Okay, minus, now I have reached here, minus minus. Now C, now the other value of C is P1 V1 raised to power gamma, so I am using it here, multiplied by V1 minus gamma plus 1. So you can see here in this particular equation, this is V2 raised to power gamma, and this is V2 raised to power minus gamma plus 1. So powers, when we add them, what do you get? Minus gamma plus 1. So the power of V2 comes out to be only 1. So you can see the power is 1 here. So it becomes P2 V2 minus P1 V1 divided by 1 minus gamma. So finally, when I write this expression, I write it as P1 V1 minus P2 V2 divided by gamma minus 1. So this is the value of the work transfer in case of a reversible adiabatic process. One more thing I would like to tell you here, and that thing is, as I told you, this is the one of the relationships for a polytropic process which is given by PV raised to power gamma is equal to constant. We can also have two more relationships for reversible adiabatic process, and these two relationships are in terms of temperature and volume, and it is given by TV raised to power gamma minus 1 is equal to constant, and the third one is uh, P divided by T raised to power gamma divided by gamma minus 1 is equal to constant. And these equations can be easily derived from the equation number 1, which is given here. Okay, we can use this particular equation to get the other two equations, so that I will let you know later later on. For the time being, you should always remember that TV raised to power gamma minus 1 is constant, and P divided by T raised to power gamma over gamma minus 1 is equal to constant. Okay, and the value of W1 to 2 is for this process is P1 V1 minus P2 V2 over gamma minus 1. Now we proceed to polytropic process. Now when we say polytropic process, it's a very interesting process. Why interesting process? Because in this case, the relationship is PV raised to power n is equal to constant. Okay, this is one of the relationships, and I can get the two more relationships like I have written for a reversible adiabatic process. Second relationship for this process could be is actually TV raised to power n minus 1 is equal to constant, and the third one is equal to P divided by T raised to power n divided by n minus 1 is equal to constant. So these are the three relationships. Now actually, what is this value n? N is known as uh, uh, mm, n is, you can say, exponent. Okay, n is the exponent, and it can have any value. It can have any value. The value can vary from 0 to infinity to minus infinity. Okay, it can have any value, so n can have any value. Now let us try to understand what is the meaning of the polytropic process here actually. So for example, this is the polytropic process. PV raised to power n is equal to constant. If I take the value of n is equal to 0, okay, so what I will do, P V instead of n I put here as 0, which is equal to constant. So V raised to power 0 becomes 1. So finally I get P is equal to constant. So it means that for a value of n which is equal to 0, the process becomes, the polytropic process becomes constant pressure process. So it's very clear that when n is equal to 0, the process PV raised to power n is equal to constant becomes P is equal to constant, which is a isobaric process or constant pressure process. Now let us see, if I take the value of n equal to 1, now what do I have? I have PV raised to power n is equal to constant. Take the value of n equal to 1. I will get PV is equal to constant. Now I know PV is equal to mRT. Now this m and r is also constant for a particular gas. So T is equal to PV divided by mR. So what do you find here? You find that PV is a constant already. So this numerator is a constant, and this value mR, this is for a particular gas, it is also constant. So If you say that this is constant C1 and this is constant C2, so I can say this is constant C2 and this is constant C1. So once again, it will give rise to a constant. So temperature is constant. So that means for somebody who wants to join, wait for a minute. Okay. Yes, but joining late. Okay. So it means when the value of n is equal to 1, temperature is equal to constant. So it means we can keep any value of n and we will get a particular process. Not necessarily that it would always be either isobaric or isothermal or isochoric. It could be any other process also. Okay, so let us see. Now we know something about the polytropic process. So let us proceed further. Now you see it. Now this is the relationship I told you in a polytropic process. PV raised to power n is equal to constant. So now there is no need to explain the derivation of it, because for the process which is PV raised to power gamma is equal to constant, you got a value of work transfer W1 to 2 as P1 V1 minus P2 V2 divided by gamma minus 1. So what is the difference between this particular process and this particular process? Only the difference of power. In this particular case, the power is gamma, whereas here the power is n. So when we will derive the expression for the work for polytropic process, what is the value of the work in that particular case? I will get W for the process 1 to 2 is given by P1 V1 minus P2 V2 divided by n minus 1. So you can derive it in a similar manner. The derivation is given here. When I will send you the PPT, you can read it from here if you have not understood, but it won't be difficult actually. If you know the integration part, it's not at all difficult. So now we have derived the expressions of work transfer for 5 processes. So I will write them here. The first process was volume is equal to constant, and the value of work transfer in that particular case was equal to 0. The second one was pressure is equal to constant, and the value of work transfer in that particular case was uh, P V2 minus V1, which is equal to M or T2 minus T1. Third one is temperature is equal to constant. I told you there are 3 equations, 8 equations, and I am writing only one equation here. P1 V1 log natural V2 by V1. The fourth one is reversible adiabatic process, PV raised to power gamma constant. In that particular case, the value of work transfer is equal to P1 V1 minus P2 V2 divided by gamma minus 1. And the last process is PV raised to power n is equal to constant. And in this particular case, the work is given by P1 V1 minus P2 V2 divided by n minus 1. So I hope this is clear to you. If you have any questions, you can ask me.
Teacher,
Yes.
if I understand well, it means polytropic process can work in all different process, because here we have temperature constant, pressure constant. It means here polytropic process has the same rule of the others process.
See, polytropic process is a versatile process. It can take the shape
Yeah,
of any other process. Okay, we can keep different values of n,
yeah,
and then we can get all these processes. Okay, so
yeah.
I am going to tell you about that only in the next few slides. Let us see now. Now we have calculated the value of n for, you can say, we calculated the value of n which is equal to 0 when the pressure is constant, I told you. Okay. And we also have calculated the value of n which is equal to 1 for temperature is equal to constant. Now, what happens when n is equal to infinity? Okay, when n is equal to infinity. So let us try to see once again. Now we have, once again, I am using this particular equation, PV raised to power n is equal to constant. So now what I have done in this particular equation, I have taken the nth root, okay, nth root. So it becomes P raised to power 1 by n by n, 1 by n. Now you see from this particular equation, now this can also be written as P raised to power 1 by n, V raised to power 1 is equal to C raised to power 1 by n. Okay. So suppose I put the value of n as infinity for this particular equation. For this particular equation, I am going to put the value of n as infinity. So what I will get? P raised to power 1 by infinity, V raised to power 1, and C raised to power 1 by infinity. And this value once again can be said to be equal to constant, because you can see, if you see this particular equation, P raised to power 1 by infinity, you will get P raised to power 0. And you know that P raised to power 0 is nothing but 1. Okay, it is 1. So you are left with V is equal to constant. Okay. So that means when I take n as infinity, the value of V comes out to be constant. That means it's a constant volume process. So for a constant volume process, you can take the value of n as infinity or minus infinity. Even if you will take minus infinity, you will get a value which is very close to 0. Okay. So once again, you are going to get a constant in any case, whether it is the pressure term, whether you use here as minus infinity or whether you use here as minus infinity, you will get the volume as constant. So for a constant volume process, the value of n is equal to infinity or minus infinity. Now suppose if I take the value of n as gamma, okay, now this is the polytropic process. So what will happen? Instead of n, I am going to take gamma. So that means the polytropic process now becomes a reversible adiabatic process. Okay, so you replace n by gamma and you get a polytropic process. Yeah, here you can see I have written the values of gamma. Gamma is equal to 5 by 3 for a monoatomic gas. I told you just 2-3 slides before, 1.666. For a diatomic gas, the value is 7 by 5, 1.4. And for a polyatomic gas, the value of gamma is 4 by 3, which comes out to be 1.333. So once again, I will tell you n is equal to 0 for constant pressure process, n is equal to 1 for constant temperature process, n is equal to gamma for PV raised to power gamma is equal to constant, n is equal to infinity for constant volume process, and n is equal to n for polytropic process. Okay, because n, this n can have any value, can have any value. It can be negative also. Okay, it can be negative also. So let us now calculate the slope of any process on PV diagram. So now we are going to see it. Now PV diagram. So the best thing is that we consider some general process which is PV raised to power n is equal to constant. Okay. So I can consider any process. Suppose I consider this particular process 1 to 2. I can say that this process is PV raised to power n is equal to constant. I can say it. Okay. Or if I want, I can also draw the process like this. If I want, I can make the process like this also. Could be this also, means any shape. So it may have different values of n. So I am not worried actually about that. Now what I can do is, from this particular equation, I can do the differentiation, because if I have to calculate the value of slope, okay, what is slope given by? Slope is, because the on y-axis you have pressure, on x-axis you have volume, okay, so the slope is given by dp by dv. You know that slope is actually dy by dx. You must have studied this in differentiation, that dy by dx gives us the slope. So here dp by dv will give us the slope. So what we will do is, we will differentiate this equation. Okay, so this is the differentiation part. I think that you know about it. uh, I think you can do it, isn't it? Can you say yes or no?
Yes.
Yes.
Okay,
Yes.
so you can do it. Okay, so this is there, so you can see it from the slides also. I have differentiated it, and then finally you can see it here, dp by dv. The value comes out to be minus np by v. Okay, after differentiation. So this is the value of the slope. Now this value of slope, this is slope. This is for any process. Any process means n can have any value. You put any value of n and you will get the slope for that particular process. For example, now once again, this is the value of slope. dp by dv is minus np by v. So it is the slope of a general process which is given by minus np by v. Now I would like to try this equation of slope on a constant pressure process. Now this is a constant pressure process because it's a straight horizontal line from 1 to 2, or it could be opposite direction also, like this. Okay, now you just see it here. If you use this particular equation and dp by dv, what is the value of dp for a constant pressure process? You know, there is no change in the pressure. So the value of dp is 0. So 0 by dv is equal to minus n p by v. So what do you get the value of n as? N will come out to be 0. So from the slope, I can get the value of n. Okay, I can get the value of n. It comes out to be 0. So I have already told you, for n is equal to 0, you will get a value of constant pressure. Okay. Now let us see the other process. If you take n is equal to infinity, okay, or rather, you know that for constant volume process, n is equal to infinity. So now let us see. This is the value of slope dp by dv for a constant volume process, and here I have shown the constant volume process. Okay, vertical line. It's a vertical line. It's a constant volume process. And I want to calculate from the equation of slope that what is the slope of constant volume process. Okay. So what I can do is, here in dV, for a constant volume process, this value will be 0. So what do you get? You will get dP by 0 is equal to minus NP by V. So this is the left hand side, which is infinity. It is equal to minus NP by V. Or I can get the value of N, which is equal to infinity into V divided by P with a negative sign. So it gives me minus infinity. Okay. So it depends upon the direction which way we are going. So it is either infinity or minus infinity. So slope for a constant volume process is infinite. Now we have known about the constant volume as well as the constant pressure process on the PV diagram. So if I am starting from here, from point number 1, I am going here. It is the constant pressure process because n is equal to 0. If I am going from point number 1 to 2 in the vertical direction, I know that the slope is n is equal to infinity. So you can see the value of n is increasing in this particular direction. So where should be n is equal to 1? I can say this is the value of n is equal to 1. I can say this is the value of n is equal to say 2, and let's say this is n is equal to 3, and so on. Okay, so if I will plot it here, I can say that uh, this is n is equal to 0, here n is equal to 1, which is for the temperature is equal to constant, it is pressure is equal to constant, here volume is equal to constant. So this is the initial state. Actually I am calling this as the initial state. Okay, and if I say that here I take the value of n equal to gamma, which could be either 1.4, 1.66 or 1.3. Okay, so this becomes a reversible adiabatic process. Okay, so this is how we can say that these are the various processes we are representing. Now we can extend these lines into uh, this direction also. So you can say this is also constant volume process. This one, volume is equal to constant, and this curve, this is a constant temperature process, and I can take this. This is n is equal to gamma. Okay, so this is how we can plot the various processes. So if we are changing the direction actually. Okay, so here I have shown all those processes in this diagram once again. I have already explained it to you. Now I would like to discuss about path function and point function. So first of all, once again, uh, I have discussed about the value of work for various processes. We have just calculated the value of W1 to 2. For which process? For constant pressure, constant volume, constant temperature, PV raised to power gamma is equal to constant, and PV raised to power n is equal to constant. And you have seen for each process, you take any process, the value of work is different in each and every case. Okay, it is not the same actually. Okay, you can see it here in the diagram. This is pressure and volume plot for the constant volume process. And what is the area under this line? Is there any area under this line? There is no area under this line. Area is 0. So the value of W is 0. And you know, for constant volume process, the work transfer is 0. This is a constant pressure process. You can see it here from 1 to 2. It is a constant pressure process. And this is the value of the work which we calculated. And you can see it here also. It's a rectangle. Okay. Here, this is the initial point. The volume is V1. Here, the volume is V2. And this is a pressure. So it becomes a rectangle. And the area of the rectangle is pressure into basically length into breadth. So here also it is P into breadth is V2 minus V1. So this is the area. You think about say constant temperature process, the value of work is different. So what does it shows? It shows something very peculiar. What is that? So this is PV raised to power n is equal to constant. This is PV raised to power gamma is equal to constant. This is the value of work transfer for PV raised to power gamma. This is the value of work transfer for polytropic. So it's very clear that it is not the end states on which the work is depending. It is depending upon the path being followed. It is depending upon the path being followed. And the path via which we move in each of these processes is different actually. You have just seen the curves. I have told you if this is the starting point, then you go along this particular path in constant pressure. If it is constant volume, you go along this path. If it is constant temperature, you go along this path. constant reversible adiabatic, you go along this path. So the paths are different. So what will be the area? If I say uh, I want to calculate the work, then I will have to calculate the area under each of these curves. Okay. So for example, this area is the for constant pressure process. If I take say constant, the first one was constant pressure. Now it is this area. If I go along this curve, this area is constant temperature. Then if I take, let us say, uh, this area, this is reversible adiabatic. Okay. And for constant volume, there is no area, zero area. So it means work is a path function. It is depending upon the path being followed. It is not a point function. Now, what is a point function actually? You should try to understand that. Now, what is a point function? Now, point function is very easy to understand. Suppose I am starting from here and I want to go to this particular point. Now, I have three paths. I have path A, I have path B, I have path C. I can go from any path from point number one and can reach up to point number two. Now, suppose this is happening in a thermodynamic system. Okay. Now, if I want to calculate the value of dP, integral dP from 1 to 2, and if I am going from path A, okay, so what is the value of dP? dP is written as P2 minus P1. Okay. Had I gone along the path B from 1B, from 1B to 2B, what is the value of dP? dP once again comes out to be P2 minus P1. You go along the path C, 1C to 2C. What is the value of dP? It is P2 minus P1. So you take any path, the final value, final answer comes out to be P2 minus P1. So that means pressure is a point function. So you don't need to worry about the path being followed. So pressure, why it is a point function? It is a property actually. Pressure is a property, temperature is a property, volume is a property. So you talk about any property, that is a point function actually. It depends upon the point function. Sorry. It depends upon the endpoints, end states, uh, in case of a point function. So properties do not depend on path being followed. They only depend on end states. For example, if I am calculating dt and integrating it from 1 to 2, it will come out to be T1 minus T2. Whether you go along the path A, B, or C, it is immaterial. So you need not to worry. That is, this is very important. That is, properties are perfect differentials or exact differentials. Okay, we call properties as perfect or exact differentials because when I am integrating this particular equation, I am getting P2 minus P1. Okay, I am getting P2 minus P1. I am getting the value in the difference actually. It is P2 minus P1. So it's a perfect differential or exact differential. That is why we use small d with the property values. That means I will be using dv, dt, dp, and so on. So all these being properties, I can use for h also, dh. Okay. And when I calculate, integrate these equations for the process 1 to 2, I will get h2 minus s1, h1. For ds, I will get s2 minus s1. What is s? S is entropy. For dp, I will get p2 minus p1. For dv, I will get v2 minus v1, and so. And this small case letters, small d, is representing the perfect or the exact differential. Okay. Now, when we think about the delta W, okay, told you I am using delta W. I used delta W is equal to PdV. Why? Why I use this is because when I am using delta, Delta means it is imperfect differential. So you can see it here. I have written work being path function depends on path being followed. We cannot write dw. Okay, I cannot write this. See here, cannot write, and I cannot write w2 minus w1 because w or the work is not dependent upon the endpoints. Okay, it is not dependent upon the end state. It is dependent upon the path being followed. So I cannot write dw. If I write dw, then it will be a wrong notion. I can't write it. Rather, we use delta w, where delta represents imperfect or inexact differential. So it's not a perfect or exact differential. What is the meaning of imperfect or inexact differential is that when we integrate this value of delta w from 1 to 2, we cannot write w2 minus w1. We cannot write. Rather, we write that w1 to 2, delta w1 to 2 integral is written as w1 to 2, or we can also write it as w from for process 1 going up to point number 2, process 1 to 2, or I can also write w1 to 2. So whenever I am writing the expression for the work, I will write either w for the process 1 to 2, or I can write w for the process 1 to 2, or I can write w for the process 1 to 2. These are the three methods, three ways in which we can represent the work transfer. Some books also write D with a cut mark over its this part. So this also is imperfect differential. So if I am writing D with a cut mark here, it is once again the representing imperfect or inexact differential. So this is a correct notation. So whether I write this or I write delta W, both these are correct. These are correct. Okay. And your time is likely to be over. So I will tell you one or few things. Now, if I calculate cyclic integral of dt, cyclic means if I am starting from point number 1, I am via path, I am going up to point 2, and then via path B, I am coming to 1. Now, what will be the change in the temperature during this cycle? That is actually represented here by cyclic integral of dt. So, this is cyclic integral of dt because I started from the point number 1 and reached back to the point number 2. So, what is the change in the temperature? It is T1 minus T2, which comes out to be 0. Similarly, you calculate for any property, that means the cyclic integral of any property, you will get 0. So, this is important, that is cyclic integral of any property is equal to 0. Okay, this I think this you try to read, and from shaft work I will take in the next class. Okay, this part you can read, and now I am finishing my lecture here. Just read it. If you are able to understand, it's okay. I hope you would be able to. Okay, so any questions till now?
I guess everything is clear. Thank you.
Okay.
Teacher,
Any other student?
teacher, yes,
Yes.
teacher.
Yes.
It means we can have many different process in 1 second.
Yes. Yes. In one cycle, you can have different type of the processes. Okay. You can have different type of processes. We will
Yes.
discuss about it. There are different cycles which we will be studying later on.
Okay.
I
Thank you.
think you must have heard about Carnot cycle, Carnot cycle. Do you know
Comment.
Carnot?
What?
I am writing it in the chat box.
Cons. Yes.
Do you know about it?
No.
No, you have not heard
No,
it.
no, no. I don't know that.
Okay.
Yeah.
Okay. So it's okay. We will be studying about all cycles later on near the end of the course. So now the time is over. Just wait. I will have to take the attendance.